Welcome to my R tutorial. We will be using the built-in iris dataset in R that is already clean and ready to go. In this tutorial, I'll try to give a good understanding of how many data science topics relate, so you can start to dig deeper on your own. To begin, first ensure that you load the proper library. After you load the proper library, let's save the iris data to an iris data frame. Now, once that is loaded, we can see that we have three different types of flowers and their related sizes. We are going to attempt to predict the type of flower from the measurement variables. In the case of a multi-class classification, we need to use a classification method that can handle more than a binary response. So in this case, we're going to use k-nearest neighbors, an algorithm that creates a nonlinear boundary by measuring the relative distance between k number of points and matching closer ones together. In the process of selecting a model like KNN, you must first consider a few things. 1. How many independent variables do you have relative to the size of your dataset? Because this is a small dataset, it is good that we only have a few parameters. A model like KNN suffers greatly from the curse of dimensionality. For example, in image classification, there can be thousands of parameters. A model like KNN would not perform well because of how it relies on relative distances between points. Now, moving on, let's ensure that we factor the dataset and particularly the species. This will ensure that R treats it as a numerical input that is measurable without giving it any relative value, meaning one species isn't greater than another, it's just different. After that, let's go ahead and split the data into our training and test set. We'll use the CA Tools library for this. Once that is done, we want to ensure that we scale our features. This is most important for a classification problem, because if you have relative different dimensions, for instance, let's say you have salary and age. Salary will be a much larger number than age, and you want to ensure that they have the same variance and standard distribution. After that, let's ensure that we can begin to build our KNN model. In this, you'll see that we have a -5, -5, and a 5. This is to make sure that we only train on the part of the dataset that does not contain the response variable. In this instance, we'll be choosing k equal to 5. Generally, k equal to 5 or 10 is sufficient for any problem without overfitting. If you want to do this more scientifically, you can implement a grid search, which is a technique that is often used to find the best hyperparameter settings. Now, once that is done, let's look at the confusion matrix. What we can see from the confusion matrix down here is that we've done a pretty good job. Ideally, we'd like to see 10s across the diagonal, but overall, we've done quite a good job. Now, let's look at the plot again. If we look over here, we see, particularly right here with the sepal width and species, that it's probably the least related to our outcome. So, let's start to feature extract. If we do a similar aspect as we did before, but eliminate the sepal width from our data, we can then see that our iris data is here, and we can again go through the same process, and then look, our results are now better. Oftentimes, this will be the case when you're training your model, because a more refined data set will give you a better relation to your response variable. Now that we've done feature extraction, we can go about feature engineering. In this case, you're trying to extrapolate from the current data that you have and build a new column or new information. In this instance, I did a sum of all the relative rows for each column. As we can see, this didn't make our data or our response any different or any worse. So, just to make sure, we should do something what's called cross-validation. In cross-validation, we'll split our dataset into 5 different parts. In the first instance, we'll train on the first, second, third, and fourth part, and then test on the fifth. And in the second case, we'll test on the first to third and the fifth, and test on the fourth, so on and so forth. What this will do at the end is give us an accuracy for each different variation of our data. As we can see, we've done pretty well overall, ranging anywhere from 87.5% to 100%, and our overall accuracy is 96.6%. I'd say that's pretty good. In the future, you can use this entire process to ensure that you get a good measure of success every time you run any model that you might see fit in the future.